The zeroth, first, second, and third laws of thermodynamics are fundamental principles that govern the behavior of energy and heat transfer. To demonstrate these concepts, we only require a few metal objects, a heating source for the metals, and, of course, a thermometer for measurements. Let's begin by heating 3 iron rods, labeled A, B, and C. We position rods A and B beneath rod C, ensuring they do not make direct contact. After heating, we measure the temperatures of all 3 rods, ensuring they are equal. Through experimentation, we can conclude that rods A and B are in thermal equilibrium with rod C. Consequently, we can deduce that rods A and B are also in thermal equilibrium with each other, despite not being in direct contact. This observation aligns with the zeroth law of thermodynamics, which states that if two systems are in thermal equilibrium with a third system, they are also in thermal equilibrium with each other. Now, let's explore the first and second laws of thermodynamics using one of the 3 rods. We'll focus on the iron rod we used, which we know to be initially heated and thus hot. If we allow it to sit for a minute, we can observe that the iron rod gradually loses its heat and transitions to a state of higher entropy. This occurs because the thermal energy possessed by the iron rod is naturally released to the surroundings, following the principles of the first law of thermodynamics. Energy is neither created nor destroyed, rather, it is converted and transferred, in our case is thermal energy, to the surrounding environment. Simultaneously, the disorderliness of the iron rod's atoms, known as entropy, increases as it moves towards a more disordered system, namely its surroundings. This process aligns with the second law of thermodynamics, which governs the increase of entropy in a closed system. These fundamental laws of thermodynamics help us understand the behavior of energy, heat transfer, and the inherent tendencies towards equilibrium and increased disorder in various systems.